Hi, my name is Mandy Wu.
My name is Kyra Movva.
My name is Daniel Kai, and we're Team Firehorses.
As someone whose parents run a restaurant, I know firsthand how the food you eat can affect your health. For cholesterol specifically, these can be foods that are high in fat content, ranging from things like fried food to fatty salmon. However, did you know that you might need some of these in order to maintain a healthy lifestyle?
For years, it's been hammered into our brains that high cholesterol poses a serious health risk for us. Diabetes, heart attacks, and strokes are just a few of the dangerous consequences that can come from not maintaining a good cholesterol level.
But cholesterol is a lot more complex than just a simple sliding scale of good to bad. It's made up of two primary components, LDL or bad cholesterol and HDL, the good kind. In this model, we aim to predict subjects' HDL levels using dietary factors and demographic variables.
To understand which variables had significant effects on HDL, we explored data from the 2024 NHANES survey. It's comprised of 1,000 adults with 97 variables each: diet, demographic, body measurements, alcohol behavior, and more. We plotted histograms and correlation heat maps to identify trends and potential biases. Most variables showed a strong right skew, which told us that there were quite a few outliers to watch out for.
A few variables like DRABF, DR1-MRESP, and ALQ111 also turned out to be constant across all subjects, so we dropped them because they wouldn't have affected our predictions anyway.
From there, we calculated the Spearman correlation coefficient for each variable. 3 stood way above the rest: the waist circumference, gender, and BMI, with R values of 0.605, 0.534, and 0.525.
For the categorical variables, we ran a Kruskal-Wallis test at alpha equals 0.05, followed by a done post-hoc test with Monfroni correction to find differences between categories and account for skewness. Anything that was not statistically significant was dropped. Then we standardized everything and split the data 70-30. After pre-processing, we tested 4 models: Random Forest, XGBoost, PLSR, and TabNet. Random Forest is good at handling large feature sets, whereas XGBoost is optimized for larger, more complex patterns. PLSR helped us manage the dimensionality from our 97 features, and TabNet is a neural network specifically designed for tabular data.
Our baseline was the standard deviation of HDL in the dataset, 9.011 milligrams per deciliter. All 4 models came in between RMSE of 5.0 and 5.9, which was already a meaningful improvement over our baseline. XGBoost and Random Forest were very similar, which makes sense given that they both use similar tree-based mechanics, but we believe that TabNet could also get us a good improvement with some extra fine-tuning.
So we fine-tuned the XGBoost using random search with 5-fold cross-validation, and the TabNet was the Optuna library. After tuning, the TabNet gave us a max CV RMSE of 5.074, which, while still an improvement, couldn't beat XGBoost. The final XGBoost model had an RMSE of 4.784 plus or minus 0.452 and an R-squared of 0.715 plus or minus 0.049. That's a 47% reduction in error versus baseline. It means 72% of the variation in HDL can be explained by our model.
What was interesting is that physical metrics like waist circumference and weight were far stronger predictors than most dietary variables.
We also considered whether socioeconomic factors like the poverty-income ratio might be meaningful predictors. That's a route worth further investigating in future work, since access to healthy food is deeply tied to income.
Our dataset was 1,000 adults, which was solid but limited. Larger datasets and deeper neural networks could help capture cellular patterns we weren't able to surface.
If we could capture time-based data, like tracking how HDL shifts over time as diet and lifestyle change, we could push accuracy significantly further. Additionally, feature engineering to combine important features like complete diet summaries into one variable might have helped us even more with our predictors.
Thank you so much for the opportunity to present our solution.
We hope this demonstrates the real potential machine learning has in making preventative healthcare more accessible.